In this video, we're going to take a look into how foundation models like GPT-4 are trained. So when we are talking about how these models are trained, there are usually three things that go into the recipe. The first is the data, right? So these foundation models, especially the language models, they're designed to emulate language. They're designed to generate language, synthesize, understand language. So in that case, we need heaps and heaps of language data. So if we want a model that can do really well at English, then we want data, lots of data, which is in English language, so that the model can learn from the data. The second thing is the architecture. That's basically the details around how the model is actually put together, how are the neural networks laid out. And the third is the compute, the training process. How do you use that data to train that neural network and effectively have it learn from that data? And also, how do you actually do that training in the server clusters that you have, right? So those are the three different building blocks, if you will, of training these foundation models. So the agenda for this video is as follows. So we'll start with data collection and pre-processing. As I said, data is really important. And then we will go into tokenization, which is a technique through which we basically break down the data into small chunks that the model can understand. Third is going to be about transformers. That's the architecture of the neural networks. The T in GPT stands for transformers. And then we will go into pre-training, right? So in ChatGPT, the P stands for pre-trained. GPT is generative pre-trained transformers. We'll be looking at the pre-training process as well. And then finally, we will see how a base model gets created, how a foundation model gets created. We will also do a quick demo of a foundation model. All right, let's get started. So how do we go about collecting the data? Obviously, we need lots of data. And to build these foundation models, we need text to train it, and we need lots of text and lots of diversity in the text, right? Why do we need that? We need that because we want the model to have a general intelligence, so that it knows about wide varieties of disciplines and domains, and also it can perform really well in different contexts. So where do we get it then? So what are these data sources? Some really popular data sources in the past have been Common Crawl, which is basically a data set of web pages. It's a web archive. There's also Books Corpus, which is basically digitized books, all of human knowledge essentially. And then Fine Web Dataset, that's another one, which is high quality web content again. Let's take a look at the Fine Web Dataset. I'm going to go to Hugging Face, and Hugging Face is a website that you're going to go to really often as an AI engineer, because they have different foundation models, different multimodal models, and variety of models, not just transformers, but other architectures as well. There's data sets as well, there's spaces, and heaps of other things as well. But for this video, we'll just take a look at this one data set called FineWeb. This is a huge data set. It is 50 terabytes plus, and it has around 25 billion records, right? And each record in the data set, here's a sample. So each record is the text content extracted from a website. In this case, this is the website. This is from washingtonap.org, and this is the contents of the page. And you can see that all the HTML tags and other markup has been stripped out, and this is just plain text. And you can scroll down. There's 25 billion of these records, and you'll see websites from all over the world going into various different topics. And there's also the source URL. There's also things like when was this fetched, and things like which language is the article written in. So language is really important, which we will look into a bit later on as well. So that was an example of one of the data sets that could be used. Essentially, during this process, what we need is as much of data as we can get our hands on, because, like I said, one of the three parameters of a foundation model is the data that it was trained on. Once we have the data, we have to make sure that the data is of a good quality, right? We don't want things like spams, ads, irrelevant things, and content that we don't want to train our model on, because these models are trying to learn from these text, and if you feed it data that you don't want the model to emulate the behavior of, then you're not going to get that. The model is going to train to the data that you show it during training. You probably also want to do language-based filtering. In the Find Web dataset, we saw that it has a language field as well. So each entry in the dataset is marked with what language that column is in. If you're training a model in English, then you probably want to filter by English datasets rather than training on datasets or websites from other different languages. And finally, once you have gotten rid of things that you don't want, then you have your cleaned and filtered data. This yet another step of data processing that is usually done when these models are trained. This is basically around removing personally identifiable information, like names, email addresses. Those show up quite a lot on blogs, articles, and generally on websites. And we want to make sure that our model does not leak information unintentionally. And then also, if there are things like syntactical errors, not syntactical, but grammatical errors, or things that doesn't make sense and we feel like is not representative of what we want our model to be trained on, then we eliminate those as well. What we're left with is still, terabytes of data, good quality data, which now is ready for training our model, right? So just let's take a pause and think about the magnitude of training data scales. So as an example, if we look at a model like GPT 3.5, then we are looking at trillions of tokens and petabytes of storage space. This is the amount of data that we're looking at, right? And that's the scale that these models are operating in, which gives them that ability to generate human-like text. There's also a concept called tokenization, which is really relevant when you're dealing with these foundation models. So what are tokens? Tokens are basically fragments of your text that you provide to the model. So models can only understand text, right? So these are transformer models, deep learning models. They work on numerical values. So they work on numerical values and they work on a lot of matrix multiplication and matrix operations, right? So what we need to do is we need to convert the language text that we saw in our training data set. We saw an example of Find Web data set, but we need to take that and convert that into a numerical representation. Why? Because our model understands numbers, not text. Okay, so that's what tokenization is. Let's see that in action. So let's imagine that we have this sentence: artificial intelligence is amazing. Now an example model might tokenize it into different components of the text. So artificial intelligence, you can see the space is also included here and space included here and so on. And then finally we convert that into a number, right? So this process, all models have their own way with which they tokenize input into numerical values, but the goal is to get to a number from a text, and this process is reversible. So you can go from the numerical representation to the text as well, not just one way. There's also tools like TikToken, which are really good to visualize this. So I'm going to bring this up. This is a really helpful utility to help you understand how your input gets broken down into tokens by a model. They let you select different model providers. Let's select GPT-4o. Let's say my query is, which direction does the sun rise in, right? And we can see that these are the tokens that were produced, and these are the actual value of the tokens that the text is made up of. Right, so that's tokenization really quickly. Now, with that, we will move on to transformers, right? Transformers is the architecture of the current day foundation models that have seen a lot of success in generating language. Originally, they were developed by Google and released with the paper Attention is All You Need in 2017. And now, most of the AI companies, most of the AI labs that produce foundation models are building it using transformer architecture. So what is so special about the transformers architecture, right? So in the transformer architecture, there are a few key components. There's a attention mechanism, which is basically allowing the model to focus on the whole text rather than focusing on just the part of a text. It's important to understand the context in which transformers came about. Before transformers, for natural language processing and generating language, these kind of tasks, RNN algorithm and LSTM techniques were quite popular. And transformers were proposed as a better way to do the same task, and they indeed met the task. And one of the mechanisms that they use is the attention mechanism. And what this mechanism allows the transformer to do is to understand the text not just by looking at a few tokens at a time from a window, but basically looking at a holistic text and the relation of one particular token to all the other tokens that you might have in the text as well, right? And there are encoder and decoder components of a transformer model. One is to understand the input, and another is to generate the output. What transformers did was they helped us do NLP really well, and it was really great for the task because of the attention mechanism. But they also made it possible to scale up our size of the model because the architecture was really scalable when you implemented it, right? Which meant that the models can now scale up to millions, billions, and even trillions of parameters. And so can the data set, and so can the compute as well. That was a really, really important thing to be aware about with transformers architecture. So just a little bit of more depth about innovations in transformers. One of them is positional encoding. So the transformer model understand not just the meaning of a text, but also where it appears in relation to other texts in the input, right? For example, when I say the word, he went to the shop and met her there. In that sentence, he went to the shop and met her there. The last there is referring to the shop, right? And we can only say that because we as humans can understand that text, and we can understand that the pronoun there is referring to the shop. And positional encoding allows transformers to essentially do that. The second is attention mechanism, and attention mechanism allows the model to focus on the most relevant parts of the text. And finally, the third is self-attention, right? So this is about understanding one particular token by looking at all the other surrounding tokens around that token. So those are the three main ideas that the transformers paper pushed, and they have been the main reasons why models like ChatGPT are seeing such success. Now, we have spoken about transformers a lot. Let's look at how a transformer model looks like. So this is in this website, it allows you to look at basically underneath the hood of some of these models. You can look at a model like GPT-2, which has 124 million parameters, or something like a GPT-2 XL variant, which is 1.5 billion, or GPT-3, which is how many parameters? Let's see, 174 billion parameters, right? We will just look at NanoGPT. NanoGPT is a I guess learning project that was implemented by I think Andrej Karpathy, and this is just a visualization of that neural network. So if we look at this, at the top is our input, right? This specific model, the goal of this model is to basically just sort the input, and let's say the input is this, the goal is for it to sort it out. So A, B, 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 C, C should be the output. So first thing that happens with these models when they are working or during inference is they first break the input down to tokens. We just spoke about tokenization, and it gets broken down into token. In this case, the token is represented by 2, 1, 0, because there are 3 different possible inputs, and they've just given it 0, 1, and 2. Now the token then gets embedded into an embedding space. What that means is the token gets converted to a long array of floating points, which represents the token in a high dimensional space. And then the way it works is your embedded input goes through each of the layers of the neural network of the transformers model, and some of these layers are attention layers, and once it goes through each of the layers of the neural network where your tokenized input, which has been encoded, gets passed through the model, and finally at the end emerges the output that you're after, right? So that was a visualization of a model, and we saw how our data gets through the model by first being converted into a input embedding, and it passes through different layers of the model, and we get a result in the end. Right. So the third part of this creating a foundation model is pre-training, or we can simply call it training as well, but the reason it's called pre-training is because there's usually another step which is called post-training as well. But essentially during pre-training, what we do is we take that model, we take that transformer model, and then we teach it how to predict the next token, right? So we have a huge data set containing millions of tokens, and what we do is we show the model bits and pieces from this data set, and we ask it to predict the next token. We ask it to take a guess, right? For example, let's say the data set contains the sentence, "The sun rises in the east." What we do is we give the model the tokens, "The sun rises in the," and we ask the model to predict east. And let's say it predicts the word, but it predicts west, right? And what we do is we basically use supervised learning to teach the model that what it did was wrong, and we ask the model to adjust its weights, adjust its parameters. And that's how the model learns and knows to reproduce the training data and understands the relationship between the data and the training data set. So how does that actually happen, right? So there are 3 things that that make this possible. First, we ask the model to make a prediction. The sun rises in the, and the model has to predict the next word, next token. If the model predicts east, then that's wonderful. Then we want to basically give a thumbs up to the model. That's the job of the loss function, right? Loss function, what it does is it takes the model's prediction and it gives a value to model, which indicates whether the model, how good the model predicted the next token. And then there is back propagation, which is now that the loss function has told me that the model did or did not perform well, how do I go from that result of a loss function and then adjust the model's parameter? That's called back propagation. This is an algorithm that was has been around for a long time and has been used in deep learning for decades now. And then finally, gradient descent. This is an algorithm that lets the model adjust its parameters so that next time around, it's slightly better at predicting the next token. So again, model makes predictions. The sun rises in the west or east. We measure the loss, which is how far apart is the prediction of the model from the expected prediction. And then we use the back propagation algorithm to efficiently calculate the gradients, and then we adjust the model parameters to make the model learn about that particular input. Right, now that we've seen the pre-training in a high level, let's talk about where that is done and what it takes to do that pre-training, right? So pre-training, we're looking at massive scale. We talked about the scale of the data set, which is in petabytes of data. We also talked about these models, and we saw that some of these models, especially GPT-3, was around 175 billion parameters. So we're talking about huge models here, right? Which means we need big hardware as well, and we need specialized hardware, things like graphical processing units or tensor processing units, and lots of them, dozens, hundreds, thousands, or hundreds of thousands. We just saw that Grok 3, the latest model by XAI, was trained on 200,000 latest NVIDIA GPUs for months, right? Sometimes it's usual for these trainings to go on for weeks or even months. And naturally they cost millions, tens of millions, hundreds of millions of dollars, and they can be prohibitive. Not everybody can do this. After that, we have the data, we have our transformer model, and we have the pre-training algorithm, which is showing the model the data and continuously learning patterns from that data. And at the end of it, what we get is called a base model or a foundation model. Let's take a look at a demo of one of the foundation models that I have. Okay, so here I've got a model called Mistral Small Base. This is a model by a French company called Mistral, and this is running in my own computer in this instance. But the reason I want to show you this model is because this model behaves slightly different than what you might be used to, right? Let's ask it a question. What is the capital of France? Usually when you are interacting with these models, you might be expecting it to come up with an answer straight away. In this case, it does, but rather than stopping there, it also says, is the answer of what is the capital of France, for which our team has given the answer with explanation after extensive research so that you won't have the trouble finding the answer, da, 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 da. So, and it goes on about another question trending in the USA. It looks like it's writing an article rather than answering my question, right? And that's how base models tend to be. That's how these pre-trained models tend to be. They haven't been trained to act like a chatbot. They've essentially been trained to predict the next token, right? And that's the behavior we're seeing here. And it's, it goes on and brings up lots of random text. If I switch that to a post-trained model, not just pre-trained, but it has also been what is called instruction fine-tuned, so that it's designed and has been post-trained to act like a chatbot. Then if I ask it the question, what is the capital of France? There you can see that this version of the model acts more like a chatbot, right? So just wanted to demonstrate the difference between a base model and a post-trained model. Now, in the next lesson, we'll look at the post-training phase of how these foundation models are built. Thanks.